Good morning. Last class, we have seen the derivation for bending stress of beams M by I is equal to sigma B by Y is equal to E by R, where M is the maximum bending moment, I is the area moment of inertia, and sigma B is the bending stress, and Y is the distance from the neutral axis, and E is the Young's modulus, R is the radius of curvature. So this is the bending stress expression. Now I can write like this: if you take this M by I is equal to sigma B by Y, M by I is equal to sigma B by Y, M is equal to I by Y into sigma B, where I can write I by Y as Z, where Z is called as a section modulus. So section modulus is a ratio of the area moment of inertia to the distance from neutral axis to the extreme outermost fiber. And for a rectangle section, we can write the section modulus like I by Y, where I is the BDQ by 12, B is the width, D is the depth of the rectangle, Y is nothing but total depth divided by 2, that is D by 2, Y is the distance. And if you just simplify, you get Z section modulus to be, for a rectangle section, BD square by 6. And for a circular section, moment of inertia, area moment of inertia is pi d power 4 by 64, and Y is nothing but total dia divided by 2. That is nothing but total depth divided by 2, that is d by 2. So if you just simplify, pi d cube by 32 is the section modulus for the circular section. So if you take the table, if you take a look at the table, left hand side you can see the beam subjected to different types of loadings. That is, only one load is acting at a time. And the right hand side you can see the maximum bending moment. Okay, here O is missing, maximum bending moment M. So simply supported beam with point load W at the middle, WL by 4 is the maximum bending moment formula to get the value. And simply supported beam with the UDL W over the entire span, WL square by 8 is the formula. And simply supported beam with an eccentric point load W, WAB by L is the formula. And simply supported beam with a couple alone at any point between the two supports, M. Okay, M is the formula. That is, maximum bending moment applied will be equal to the maximum bending moment, right? That is, maximum bending moment, or a couple acting on a beam is nothing but the maximum bending moment M. Cantilever beam subjected to a point load W at the tip, W into L is the maximum bending moment, and cantilever beam subjected to UDL W over the entire span, WL square by 2 to find the maximum bending moment, and cantilever beam subjected to a couple M alone anywhere along the length of the span is given by M. Okay, so couple, if couple, only one couple is acting, means that would be equal to the maximum bending moment for the given beam. Okay, so these are the ready-made formulas available, so that these are the values for M that we can use it in the bending stress expression in place of M. Okay, so if the beam length is given, point load is given, UDL is given, whatever it is given, you just M value stands for all these types of beams with the loadings. Okay, individual loads acting. Okay, if combined loading is acting, means I'll tell you how to do find the M. That is, M is nothing but the maximum bending moment. So now I have taken a problem from a strength of materials textbook by R.K. Bansal. Thanks to the author. These are the exercise problems. Okay. So a steel plate of width 60 millimeter and of thickness 10 millimeter is bent into a circular arc of radius 10 meter. Determine the maximum stress induced and the bending moment which will produce the maximum stress. Take Young's modulus 2 into 10 power 5 Newton per millimeter square. So write down the given data. Okay, so width B is equal to 60 millimeter, thickness 10 millimeter, radius is 10 meter, and Young's modulus 2 to 10 power 5 Newton per mm square. So this is the expression for bending stress. M by I is equal to sigma B by Y is equal to E by R. So Y is nothing but thickness divided by 2. Okay, here in this case, thickness T by 2 5 millimeter. I is equal to BT cube by 12. Okay, you get the value 5000 mm power 4. So after getting this Y value and I value, E, everything, substitute here, you get the bending stress to be 100 Newton per mm square. Then we know M by I is equal to sigma B by Y. Okay, I is known, Y is known, sigma B just now we got it. Substitute here all the values. You can find M, which is nothing but 100,000 Newton millimeter, which can be written as 100 Newton meter. Next problem. A cast iron pipe of external diameter 60 millimeter, internal diameter 40 millimeter, and of length 5 meter is supported at its ends. Calculate the maximum bending stress induced in the pipe if it carries a point load of 100 Newton at its center. So this is nothing but simply supported beam subjected to a point load W at the middle. Okay. So this is the expression, usual expression, m by I is equal to sigma b by y. So y is nothing but depth divided by 2. Here the total depth is d naught outer dia divided by 2, 30 millimeter. And I is pi by 64 into d naught power 4 minus di power 4, which is coming out to be 510,508.8 mm power 4. So m is nothing but WL by 4. You know the value of WL is known. You can find out 125,000 Newton millimeter. Now you just plug in all the values m, I, y in this, you will get sigma b to be 7.345 Newton per millimeter square or 7.345 megapascal. Next problem. A rectangular beam 300 millimeter deep is simply supported over a span of 4 meter. What uniformly distributed load per meter the beam may carry if the bending stress is not to exceed 120 Newton per mm square. Take I is equal to 8 into 10 power 6 mm power 4. So the usual expression m by I is equal to sigma b by y, and y is depth divided by 2, 300 by 2, 115, and m simply supported beam subjected to UDL. Formula, maximum bending moment formula is WL square by 8. We have to find the small w UDL. Length is given. So m by I is equal to sigma b by y. Substitute m here, WL square by 8. Okay, so I is nothing but it's given in the problem, and y is d by 2, which is 150. Sigma b is given in the problem 120 Newton per mm square. So in this expression, only one unknown is W small letter WDL, which is nothing but 3.2 Newton per millimeter. So in the problem it is asked that you have to find out UDL per meter. I can write this as 3.2 kilonewton per meter. So if you just convert the kilonewton to Newton, multiply with 1000, and meter to millimeter, multiply with 1000 will get cancelled. So I have written 3.2 Newton per millimeter. Okay. So you can write 3.2 kilonewton per meter or 3.2 Newton per millimeter. So next problem, a cast iron cantilever beam of length 1.5 meter uh, fails where a point load W is applied at the free end, and the section of the beam is 40 millimeter into 60 millimeter, and the stress at the failure is 120 Newton per mm square. Find the point load applied. So m by I is equal to sigma b by y. So this is a cantilever beam subject to point load at the tip. W into L is the maximum bending moment. Y is d by 2. Okay, 60 by 2, that is 30 millimeter, and I is equal to BDQ by 12, 720000 mm power 4. So m by I is equal to sigma b by y. So m in terms of W into L, capital letter W. So you are getting the value to be 1920 Newton. So next problem, a timber beam is 120 millimeter wide and 200 millimeter deep and is used on a span of 4 meters. The beam carries a UDL of 2.8 kilonewton per meter run over the entire length. Find the maximum bending stress induced. So these are the given data as length 4 meter, width 120 millimeter, depth 200 millimeter, and UDL is 2.8 kilonewton per meter or 2.8 Newton per millimeter. Okay, that 1000 on the numerator and denominator will get cancelled. So you can write it as 2.8 Newton per millimeter. So m by I is equal to sigma b by y. So y is equal to d by 2, depth by 2, 200 by 2 is 100 millimeter, and m is equal to WL square by 8 because simply supported beam subjected to UDL for the entire length. So maximum bending moment is WL square by 8. So m by I is equal to sigma b by y. Sigma b is 7 Newton per millimeter square or 7 megapascal. So next problem, a timber cantilever beam of 200 millimeter wide and 300 millimeter deep is 3 meter long. It is loaded with a UDL of 3 kilonewton per meter over the entire length. A point load of 2.7 kilonewton is placed at the free end of a cantilever. Find the maximum bending stress produced. Okay, so a cantilever beam, okay, over the entire length, 3 kilonewton per meter UDL is acting. In addition to that, a point load is also acting at the tip of magnitude 2.7 kilonewton. Okay, so we have to find out the maximum bending stress. Okay, so now this is here we have to consider two conditions. Cantilever beam subjected to UDL over the entire length, maximum bending moment formula is WL square by 2. WL square by 2. Okay, cantilever beam subjected to point load at the tip means W into L. So in place of M, okay, in place of M, you have to write down WL square by 8 plus W into L as the maximum bending moment. So this is the formula. Just I have written in terms of section modulus, where I by y is the section modulus, which is nothing but BD square by 6, so that it would be easy for us to solve the problem. So M is equal to Z into sigma B, where Z is BD square by 6 for a rectangular section. For a rectangular section. Okay. So M is equal to WL square by 2 plus W into L plus W into L. So this M value we have to substitute here. Okay. Okay. So after substituting here M value and BD value, you get sigma B to be 7.2 Newton per millimeter square. So here a timber beam is freely supported on supports 6 meter apart. It carries a UDL of 12 kilonewton per meter run and a point load of 9 kilonewton at 3.5 meter from the right support. Design a suitable section of the beam, making depth twice the width if the stress in timber is not to exceed 8 Newton per millimeter square. So here simply freely supported means simply supported beam of length 6 meter. Okay, it is carrying UDL 12 kilonewton per meter over the entire length. In addition to that, point load of 9 kilonewton is acting at a distance of 3.5 meter from the right support. From the right support. Okay, now we are having the combination of UDL as well as the point load. So how to determine the M value, the maximum bending moment value? So first we need to plot the shear force diagram. Then we have to locate the zero shear force location. Then about that section, we have to write down the bending moment expression. Then we have to substitute the value of zero shear force location in the bending moment expression to determine the maximum value of bending moment. And that bending moment value must be substituted in place of M in the expression M by I is equal to sigma B by Y. Okay, so we know how to take the moments and determine the support reactions. So we have taken the moments 9 into 2.5 clockwise positive, 12 into 6 into 3 clockwise positive, and RB into 6. So RB is 39.75 kilonewton and sigma Fy is equal to 0. RA plus RB, upward is positive, downward is negative minus 9 minus 12 into 6. So RA is coming out to be 41.25 kilonewton. Now plot the shear force diagram. So 41.25. So from left upward is positive. So it's a point support reaction shown by vertical line 41.25. From A to C, UDL is acting. So nature of the shear force is an inclined line. So this length is 2.5. So 12 into 2.5. So 41.25 minus 12 into 2.5 is nothing but 11.25. Then once you reach the point C, 9 kilonewton is acting downward. So 11.25 minus 9 is nothing but 2.25 positive. Okay, positive. If you stop there and you just proceed from right hand side, from right upward is negative, right? Sign convention, as per sign convention. So 39.75 acting downward. Just draw the line. Then you simply connect these 2 points. You don't have to bother because same UDL is acting continuously between B and C. You can simply draw by a straight line or connect by a straight line. So this is a zero shear force location. Now I want to find out this location. Okay, zero shear force occurs between C and B, or in other words, maximum bending moment occurs between C and B. So how to determine this location? We have to write down the expression about XX. shear force expression. Okay, right side of the section, upward is negative, downward is positive. Okay, so 12 into x minus 39.75. So equated to 0, you get x to be 3.3125 meter. Okay, this is the location of zero shear force or location of maximum bending moment. Now about the same section, try to write down the bending moment expression. Okay, 39.75 into x anti-clockwise, right side positive, and 12 into x by 2. Okay, clockwise negative. So this is the bending moment expression. In place of x, substitute this 3.3125 meter to obtain the maximum bending moment. So the maximum bending moment is coming out to be 65.83 kilonewton meter. 65.83 kilonewton meter. Now bending stress given in the problem 8 Newton per millimeter square, and the depth is twice the width. It is given in the problem. Okay, depth is twice the width given in the problem, right? You can see here. Uh, Design a suitable section of the beam making depth twice the width. So D is equal to 2B. And for a rectangle section, bending moment expression is M is equal to Z into sigma B. Z is BD square by 6 section modulus. So substitute this D here, you will get 4 B cube by 6, which is nothing but 2 by 3 B cube into sigma B. Okay, then substitute this M, which is nothing but 65.83 in this expression. Okay, sigma B is nothing but what is the value? 8 Newton per mm square. You have to substitute this M in terms of Newton millimeter. So 65.83 into 10 to the power 6, that is kilonewton to Newton multiplied by 1000, meter to millimeter multiplied by 1000. So 65.83 to 10 to the power 6 is equal to 2 by 3 B cube. Sigma B is 8. So from this we have to find B value 231 millimeter. Then D is equal to 2B, which is nothing but 462 millimeter. Now we have obtained the cross sectional dimension for the given beam with respect to the given loading. Thank you.